Hi, today I will be answering a concept in atomic spectroscopy. So the problem goes, why are higher resolution monochromators found in ICP atomic emission spectrometers than in flame atomic absorption spectrometers? So to answer this question, we must first understand what is optical emission spectroscopy and flame absorption spectroscopy. So optical emission spectroscopy, the principle behind this one is when a plasma energy is given to an analysis sample from outside, the component elements or the atoms are excited. When these excited atoms or the ionization process returns to its ground state or the low energy position, it will emit emission rays or spectrum rays and are released, and emission rays that are correspond to the photon wavelength are measured. So these measured photon wavelengths are interpreted as spectral lines, which is corresponded to a specific element. So different spectral lines will be given detected through the detector, which corresponds to the specific element. So the what happens in this optical emission spectrometry is that to generate the plasma, first the argon gas is supplied to the torch coil, which is this one, and then a high frequency electric current is applied to the work coil at the tip of the torch tube, which is this one. So from there, using electromagnetic field created in the torch tube by the high frequency current, argon gas is ionized. So from here, the ionized argon gas is going to be generated. Thus, the plasma would be formed. So for the sample will then be put into a solution, which will be sprayed by the nebulizer through the plasma, wherein the ionization would take place. From here, the high electron density of with the high temperature of 10,000 Kelvin, the plasma would then be atomize the sample as well as the argon gas, wherein the light produced here would be passed through the transfer optics. So here we have two, which would then be read by the spectrometer and would be passed onto the computer interface, wherein the data would be analyzed. From there, the spectral lines would be produced from the optics, would be interpreted whether from prior data of the elements that corresponds to the spectral lines produced. So for optical emission spectroscopy, there are two views. The first view is the radial plasma view, wherein it offers a less sensitivity than the axial view. So in radial view, the transfer optics is opposite the transfer optics, while in the axial plasma, the plasma would be adjacent to the transfer optics. So what are the difference between these two? So in radial plasma, it has less sensitivity than the axial view. However, it is preferable for analyzing difficult samples such as organics or very high dissolved solid matrices. The plasma viewing position can be optimized to reduce background emissions. While in axial view, configuration offers great sensitivity than radial configuration, but has higher susceptibility to matrix interference as the entire plasma is viewed, increasing the quality of light observed from both analyte and background emissions. So basically what it says is that the concentration of the light that was passed through in axial plasma is greater than the radial plasma, hence the amount of light reflected in axial plasma is far greater than the radial plasma, wherein here, since there is a higher quantity of light that was shown this would now create interference such as the background emissions, which can be coming from the sample or the argon gas. Another one is in contrast, the flame absorption spectroscopy principle is when a sample solution is aspirated into the flame, the solvent is vaporized, leaving particles of solid salts of the sample. So what happens here is that the sample, as same as the optical spectrometer, the sample would be sprayed through the use of the nebulizer into the flame, wherein the solvent would be evaporated and will be left with the solid salt of the sample. The salt would then burn and convert it into gases form, which is dissociated into free neutral atoms, or went into ionization, and some of them excited by the flame heat. Remaining atoms in the ground states would then absorb light coming from the hollow cathode lamp, which would transmit radiation that would shine and then would pass to the monochromator, wherein specific wavelength would then pass to the detector depending on what depending on the analyte that is being observed, and the wavelength of specific wavelength emitted, and then the intensity of light absorption is measured. So what is the difference between flame absorption and spectrometry principle and flame absorption spectrometry? Where here in flame absorption spectrometry, we can only find one specific sample or analyte, since the flame does not have the same temperature as that of the emission spectrometry, optical emission spectrometry. Here, we can just find the easier to ionize, such as the alkali metals in determining. So, also, we will need to define what is a monochromator. So, according to Chemical Dictionary 2017, it is an optical system that transmits a specific band of electromagnetic spectrum. So, bands are the lights that was reflected as it passes through a monochromator, wherein this could either be a prism or capability of which is capable of refraction, and diffraction grating, which is capable of diffraction. Typical applications of monochromators are isolation of a narrow band of radiation from a continuum light source for absorption measurements or analysis of emission from excited atoms or molecules. So from here, we know that the use of monochromators and spectrometers is just to differentiate, to isolate specific wavelengths of reflected light. So here, the process would go a broad spectrum of light. This can either be a halogen or incandescent light, and then it will shine through a sample. And then some colors are absorbed more than others depending on its composition. Then this monochromator would be specifically the diffraction grating splits, which is commonly used in the spectrometers, split the colors so that they can be measured separately depending on the sample that or the analyte that we want to observe. So using a webcam or a detector, we can measure each color in graphs and their intensities compare it to known samples to understand which element or ions that we want to know from air. So from here, we can therefore conclude to answer our problem that's spectral interferences, or the difference in the lines that was produced as by detected through the light shown from the intensity from the monochromator. We can conclude that the common The spectral interference can be common in high temperature plasmas as opposed to flame-based systems given the complete excitation and subsequent emission of all compounds in the sample, including the argon. So what it basically says is that the temperature of plasma is far higher than that of these flame-based systems. In here, it can shine, or it can excite or ionize far too more samples, wherein it produces spectral interferences, since it has also excites or ionize the argon gas, compared to the flame base, which only ionize specific and easily ionizable substances such as alkali metals. And because in ICP, the selectivity and resolution of emission is fundamentally coming from the monochromator. Therefore, having higher resolution monochromator provides a better performance in isolating the analyte spectral line from the background emissions. So, this is why we need higher resolution monochromators in order for us to isolate the analyte spectral line. So, we would be able to choose which is the best wavelength from that, so that we can separate the analyte from the matrices or the background emissions. Unlike in flames, atomic absorption, it is only used to isolate emission line of analyte elements from line impurities in the field gas and from background emission of atomizer. As prior, we know that the flame base only absorbs the specified analyte. So these are just a few of these references. And for that, I thank you.